Okay, just started the recording. So this is um, sharing the presentation here. Um, get myself set up quickly here. Okay. So today's lecture is about the um, usage of matrices and tensors in neural networks. Okay, and we will see the motivation for that. Let's first of all, this is the outline of this lecture. We will explain what tensors are. I'm going to go through a example, numerical example. I love numerical examples because really they kind of give me the true explanation of the theoretical issues that we discuss. Okay, so just a quick definition here. Tensors can come in zero zero way, okay, which becomes a scalar here. Okay, you can have one way. Okay, when you have a vector here. Okay, so a scalar, a vector. You can have two ways. Okay, tensors, and this is a matrix, or you can have a three-way here, or four-way, etc. In general, we would like to stick with, the how many ways here if we use this n here. We would like to use the conventional name of a scalar. And we have, when we have one way here, would like to use always vector. And when we have conventionally, when we have two dimensions, we say matrix. But above that, okay, above that, we would use the name tensors. Okay, so tensors really, in general, they are n-way arrays or n-dimension arrays where n is greater than or equal to 3. You might find somebody who slightly disagree with this definition, but this is the definition we're sticking with. Okay, all right. So for example, here we are giving examples of vector, of scalar, of vector, okay, and how we assign their values. So I'm assuming we have a vector here, and we are assigning the third value of this vector to a value of z, okay. And here, if I have a matrix, I access the element by identifying the row and the column inside the matrix. And if you have a tensor, then you have really to give the all the coordinates for the element inside that tensor. So for example, right here, okay, I have to give the if I want to access an element, for example, here, I'll have to give the row, the column, and the depth, all right, where that element lives. Now, if I have a tensor of 4 dimensions, now I'll have to use these coordinates to identify and then assign to an element inside the data, which is a tensor. Okay, so this shows me how I access these elements. Okay, if you are into programming languages, these kind of things, you understand them very well because this is how we access elements in multidimensional arrays. Okay, all right. So really, the motivation of using tensors and matrix notation is neural network. If we express them in equations, if we express them in equations, they become really messy. Okay. Oh, gotta uh, see if I can get my page back. All right. They become really messy if we express things in individual equations. So tensor notation really simplifies the expressing the behavior of the neural network, whether it's a forward pass or back propagation. And we will see through a simple example how we will simplify those equations. Okay. let's pick this example, right? I have a neural network of very simple, and we will see how equations can get messy even with this simple neural network. We got our two inputs here, x0 and x1. We have two outputs, f0 and f1. Okay, so two inputs and two output neural network and a hidden layer here. We have node 0, node 1, and neuron node 2. We're going to assume ReLU activation function. I'm going to reference it as R here. And we have biases here, B1, B0, sorry, B1 and B2, right? And we have the output coming from these hidden nodes or hidden layer nodes, Z0 and Z1 and Z2. All right. Then we've got these weights, right, which are connecting or on the connections between the inputs and the hidden layer. Those are the A's, A0 and A00 and A01. And the convention is when we say Aij, it is the way that is between the ith receiving node and the jth producing node. Okay, so in this case here, if you look at this A2 to 0, right? The 2 referencing node 2 and the 0 referencing x0. Okay. All right. And then also these B's as well, they are on the connections between the hidden layer and the output nodes. All right. So just this example, we'll use it in uh, the next explanation. If you are listening up to this video and you haven't fully understood this example, please pause the video, look at this structure of the neural network, okay, which is simple really, because we're going to use it in the next explanation, right? Try to grasp all the concepts, number of nodes, the outputs, the inputs, etc. Okay, now we can express using matrix notation. We can express the inputs and the outputs of this and the parameters as well. So, for example, if I have these are x0, x1 can be represented by this matrix. Okay, so these are the input the input values matrix, and the output can be represented by an output matrix. Okay, where I express the first output and the second output. Also, these parameters, the A parameters, which connects the input layer with the hidden layer, can be also expressed in terms of matrix. Notice that the first row represent the no the weights of the connection that is going to this node. The second row represents, let me choose another color here. The second row represents the connection that goes to this node. Okay, and as we have agreed, this is the convention. And the third row here represent the connections that goes to this node. Okay. And also we can have a matrix for the biases, or a vector, I should say, for the biases. And this is B0, B1, and B2. And this is they are right here. I can represent the outputs coming from the hidden node in this vector. Okay. And I can represent as well the weights for the connection between this layer, hidden layer, and the output layer in these B's. And this is the matrix here. Okay. Again, I want you to understand what is the notation here. The first row here goes to the connection that goes to the first output node. Okay. And the second row here, this is the second row, goes to the connection that feeds this node here. Okay. We can see B10, B11, B12, oops, sorry, B10, okay, B10 and B11 and B12. All right. All right. Now, let's see. All right. Did I flip? All right, too quick? No, I'm good. All right. So now we can express the operation of this neural network, and obviously, the neural network, every node here is producing an output Z. So node N0 is producing Z. Let me choose a different color here. Probably the blue is the safest. Okay, so the N0 producing Z0, and this is the equation how we do it. We multiply the weight, okay, times this X, the input X, and the next weight times X1, okay. These two weights feeds to this node. Then we add this bias, then we apply the ReLU function. Then we produce the Z0. We're assuming the ReLU function as the activation function. Okay, similarly, Z1, by the way, if you have uh, trouble understanding these equations, please review the earlier lectures regarding the inference and forward evaluation of the neural network and also the training of the neural network. I'm assuming that you have listened up to those videos and you understand these equations. Similarly, Z1 and Z0. Now, those are these outputs right here. Now we can express them in terms of a vector here, which is equal to, this is a ReLU function, is applied to what? Well, this matrix here is multiplied with this matrix, with this vector, which is x1 and x0, and add to it the bias. Okay? All right. So in matrix notation, we will see that this is how we express it. This is vector Z. This is matrix A. This is vector X of the input. And this is vector of the bias. Okay. So this is a matrix notation right here. Right. So you can see the difference between this is complicated. Right. This is complicated, right? It has, and even with a small neuron, but this is what? This is, let's see, clear and simple, right? Simple in terms of how we represent these equations. We don't get messy with too many variables. So that's the purpose why we explain matrices and tensors in the training and inference of neural networks. They simplify expressing the equations. Okay, now next we'll see how we can express these outputs, which is F0 and F1. These are their values, right? These are their values. So take a look at the F0, for example. You have to multiply the output Z0 by this weight and Z1 by this weight, this B0, and Z2 by this B weight, and then sum them up, and that is the value of F0. And similarly, F1, and we can express this in terms of equation by F vector here equals the multiplication of the B matrix times the Z vector, which is can expressed right here in simple format. Okay, so now I have expressed evaluating the Z's and these output nodes in simple matrix forms. Okay. Now, so this is what we have done so far. Okay, so this is the Z, the output, expressing the Z, expressing the F, okay, using the output generated, which is here. This is the Z, okay. All right, this is the Z. Now we can really what we can do is that we can substitute this value here instead of this Z variable, and then I get the full equations of the F. So the matrix of the output equal the B matrix multiplied by the output of ReLU, and inside this ReLU I multiply the A matrix times the input vector plus the bias vector. Now, this simple, straightforward, this is the full math that I do for it. And you can see the mapping here. Okay, this is the output vector. This is the weights, the B weights matrix, and this is here the A weight matrix, and this is here the input vector, and this is here the bias. Okay, so obviously, clearly, the matrix form a lot simpler and cleaner. Okay, although we are doing the same math, but in the matrix notation, really what it does is it abstracts all these complexities. Whoops, sorry. All these complexities. Okay, and abstracting helped me a lot. Okay, so let's just get a numerical example. Okay, so what do we have here? In this example, let's see. Um, I'm assuming that I have this input matrix, okay, or vector, which means that this value here -2 and this value here is 1, right? That's what it means. And then I have this A matrix here, which is for the weight, which means that this value here is 1 and this value is 2. This value here is 3, 4, okay, because we know that this is for the n0, this is for the n destined for n1, and this is destined for n2. So 5 and 6, okay, and these are the biases. This is 3 here, this is 4, and this is 6, right? And then the B and the B matrix, we know that this is for the first output node, 1 minus 1 and 2, and then minus 1 and 2 and 1. Okay, so these are some, but I'm I'm expressing everything in terms of matrix notation. This is my expected output. Okay, I'm expecting here a y equals 4, a y0 equals 4, and a y1 equals 5. Okay, I'm going to assume the learning rate of 0.1. This is going to help us and then this is the how we update the parameter, the learning rate times this factor which is coming from the integration. So we'll say that we're gonna just multiply by this factor. Okay, k number of training patterns. In this case, we're gonna assume just one training pattern. Okay, which is this one. This is my only training pattern here. So I'm gonna evaluate this. And let's see how we can evaluate them. Well, we know that we have learned these matrix notation. So first of all, we're gonna compute those z's. So we know that the z's from the equations that we have. Recall these are the values that I have. Okay, these are the values from my example on the previous slide. So how do I compute z? It is we multiply the A matrix, okay, times the x plus the bias. Okay, so plug in the numbers now. Okay, plug in the numbers, plug in the numbers, plug in the numbers. So you multiply these two matrices, you get this matrix, you add the plus the bias matrix. This is the result. Okay, and if you apply the ReLU on this, then you get the same values because all of them are positive, which means this is the value of the Z matrix, meaning that you have 3, value of 3, value of a 2, and value of a 2 as well. Okay, now we take this value, all right, we know that to get the functions here, right, we need to apply this matrix multiplication, which we just derived a few minutes ago, okay, or presented a few minutes ago. Well, we multiply the mean B matrix times the Z's that we just calculated. This is the B matrix. It's given from the question, by the way, and here it is. I'm just plugging what I'm given. And here is the Z matrix, which I just computed. Multiply the two, and I get here the value of the output, 5 and 3. Okay, all what I'm doing here, I'm doing matrix multiplication to evaluate the F using the matrices that I presented few slides ago. Right, so what I have done, I did the forward pass for this network, given these input values and parameters. Okay. All right. So I got an output here of 5, an output here of 3. All right. Now, what we want to do here, we finished forward inference. What we want to do is training. Okay. And here I want to make sure, I'm going to repeat what I said. If you have not attended the class of training or watched the training video, please do it now, because what I'm gonna build on that lecture. Okay, so there what we did, we discussed that we have to compute those derivatives, right? Which is delta L over delta F. And we said the value of those is the expected value, which is Y0, right? Minus the calculated value. Similarly here, delta L over delta F1, expected minus calculated. Okay, so what we're gonna do is that we're gonna give those. This is a notation, the G matrix. So the G matrix actually equals what? Equals the error from the first output node and the error from the second output node. Okay. Now, what we want, as we have learned from the previous training classes, that we would want to propagate this error back to the down or back to the earlier layers, because propagating the errors will help me to fine tune my parameters. Okay, so I'm interested to compute delta L over delta P. Well, delta B, because I want to update those parameters as well. Okay, so you work the math, you will see that this obviously the delta L and delta B will be similar to those equations that we derived in the training class. So you will see that for delta L over BB0, which is this parameter, equal Z0 times the error G0, which is Y0 minus F0. And if you derive with respect with B delta L with respect to delta L with respect to B delta B01, you will get Z1 times G1. With delta L with respect to B02, you will get 02 G0. Okay. Similarly, we apply the same derivative, right, on B10, B11, and B12, and we'll get Z0 G1, Z1 G1, and Z2 G2. All right, again, we have explained how these equations are derived in an earlier exam in the training lecture. What I want to do here really is not to derive those again. I want to express this here now in a matrix notation. So I'm going to simplify all of this and say this delta L over delta B equals this matrix here. In fact, I'm going to simplify it more and say this delta L and delta B, this is really a matrix between multiplying G matrix with Z. And I know that the Z is a vector, right? A Z is a vector, right? Okay. But it is a vector where I have one column and 3 rows. But here I need one row and 3 columns. So this is really the Z transpose. So the delta L over delta P is the error matrix, right? Which is G0 and G1 multiplied by the transpose of the Z matrix. Okay. See, this is exactly what I did, all this analysis to arrive to this point. Okay. I now expressed the error in these parameters, okay, in terms of a simple matrix G times multiplied by Z transpose. Whoops, sorry. Did I, okay, Z transpose. Okay, very simple matrix multiplication. Again, the goal and the objective of this lecture is to show you that using matrix and tensor notations simplify expressing the equations in the inference and the back propagation. Okay, so this is in terms of these parameters. Let's see what else we can simplify. Now, I can also express those I need those z's I need to compute delta L over delta Z for them. And delta L over delta Z, again from the previous class, we can arrive to these equations. And this is nothing but multiplying the B matrix transpose times the error matrix, which is the G here. Okay, and we know what is G0. G0 equals Y0 minus F0, expected minus computed. And the G1 equals Y1 minus F1, the expected minus the computed. Okay, so delta L over delta Z, all right, equals B transpose G. And this is the B matrix which represents those, right? Now, this is a very simple matrix equations. And that, again, abstracts what is going on in terms of multiplication, in terms of equations. All right. Now, next, what do we want to do? Okay, so this is what we arrived to it from the previous slide. Okay, now we're going to assume that this delta L, okay, uh, this delta L over delta Z is really this error being propagated to this. If you make a line here, okay. So much like here where we have this G was the error going to this layer here, this delta L over the delta Z is the error being propagated to this layer. Okay, and for that, okay, so we need to multiply this G input here. Okay, we need to multiply it by this equation, and this would create for me. Let me just see if I have something that I derive. Okay. Um, let's see. Okay, so we can perform similar derivations. Okay, if I want delta, let's see, delta L over delta B, right? Which is basically I want to compute the delta L over delta B here. The small b's, they are the biases. Okay, this is equal to delta L over delta Z times delta Z over delta B. Well, delta L over delta Z, okay, I have computed it already, and I'm left with delta Z over delta B, which is, if you do the math over here, okay, it is equal to the since this is an output of a ReLU, okay, what is the output of a here? This output is an output of a ReLU. If I derive it, it becomes this h function, which is the step function. Okay. Okay. So now delta Z over delta B, it is delta L over delta Z, the step function for the A matrix times X matrix plus B. And therefore, this is what we're going to refer to as G input here. Okay, so delta L over delta Z, which I computed in the previous slide, times this step function here. Okay, and the input to it is, sorry, the input to it is the A matrix times the X matrix plus B. Okay, now if we want to sort of simplify this, then um, delta L over delta B, meaning the errors that we or this derivative that is required to be used to update those biases is equal to G input, where G input is evaluated in this equation. Delta L over delta Z times the step function of the value of these nodes. Now, how about if I want, now I computed the errors, right? The delta L over delta these B's, the biases. How about if I want to compute the delta L for the delta A? Again, I need those because I need to update the parameters. Now, if we work out the math, we will see that this delta L, okay, we'll work out the math, we'll see that the delta L over delta A is the G input, okay, which is, this is the value of it, times the X transpose, where the X is X0 over X1. Okay, and we can work out the math here and we'll see that this really X is coming from this derivative, right? When we worked on the biases, when we derived with respect to B, that this function changed to H, right, without anything. But when we do with the for A, and we derive with respect with A, then this X, right, comes out here and it becomes X transpose, and X transpose because, you know, when you multiply matrices, you have to align their dimension. This is not a derivative here. This is really what it says, a transpose, right? Okay, so instead of having this x0 and x1, we need to have x0 and x1. Okay. All right. Now, let's take examples, see if this is going to be um, okay. Um, here is what I meant by X transpose, right? I want to just to so X really minus 2 and 1. X transpose is not, this is not derivative sign. This is means it transpose minus 2 and 1. Okay, so let's go back to where I stopped. Sorry. Okay, now with all these equations derived, let's go back to our example right here. And what we want to do, we want to do training, but using the matrix notations that we derived. Now, of course, we're gonna evaluate we have done the forward pass, right? And we come with these output values. Now we can compute the error matrix here. So basically, it's expected, right? Expected minus what we have computed. Expected minus we have computed. So this G matrix is minus 1 and 2. Okay. Now, delta L over delta B is what? Is G times the Z transpose. So we do this multiplication here, and we get minus 3, minus 2, minus 2, minus 4, 4, 4. Okay. Now, the B matrix, which is this one here, now need to be updated, right? It need to be updated. How? The new values will be the old values. This is the old values of B, right? Plus learning rate 0.1 times 2. This is coming from the derivative of the loss function. Delta L over delta B, which is, this is what we have computed, right? So you plug in all the numbers and you get this is the new value of the B matrix based on what? Based on this input and this expected output. Okay, so we need to update. Now this becomes now the new value of the B matrix, right? Okay, now let's continue. So how about what's the updated value, or what's the error delta L over delta Z? What we derived earlier, that it is the transpose of the B matrix times the error G0, G1. So We get that. Okay, so notice this is the B matrix. Okay, this is the B matrix, right? Right here, but we want to do a transpose for it. This will do transpose times this error matrix. Okay, and we get this. So delta L over delta Z is minus 3, 5, and 0. Okay, now let's go continue. What we want to do is we want to continue compute this G input here, which is delta L over delta Z, which we computed in the earlier slide, minus 3, 5, and 0. Okay, so this is here minus 3, 5, and 0. Okay, all right. Multiply by A matrix multiplied by X plus the bias, and then we apply the step function. Okay, when we do that, we get 3, 2, and 1. We apply the step function. The step function means if you have a negative value, the value is 0. The step function is like this. So just to remind you with that, because we talked about it in the training. Okay, this is the step function. So if the input is negative, the output of the step function is 0. If the input is positive, the output of the step function is 1. So now we have 3, the output of it is 1. 2, the output of it is 1. 2, the output of it. How we got these numbers? Well, we evaluated this matrix. Okay. Now, this multiplication here is not matrix multiplication. It is what we call element-wise multiplication, which means this with this, this with this. This is not a matrix multiplication. Now we do that and we get the G input. This is the value of it, minus 3, 5, and 0. Okay. All right. Now we take that and we know that the delta L over delta B, this B, the biases, is equal G input. So this is the delta L over the delta B. Now I can compute the new value for delta B, for the biases. So the new value equals what? Well, equals the old values, right? Okay, these are the old values right here. These are the old values. Okay, plus learning rate 0.1 times 2 times what I have computed, delta L over delta B, which is this one here. Okay, you crunch the numbers and you get the new value of the B, right? The new value of the B is 2.4, 5, and 6. 2.4, 5, and 6. Okay, now let's continue, and we need to compute the new values of A. So this is these are the weights here. We want to compute their new values after the training pattern. Okay, so delta L over delta A equals G input times X transpose. Okay, we do this multiplication, we get this result. Okay, so and then what? The new value, old value, this is the old value, plus learning rate, which is 0.1 times 2 times delta L over delta A, which is I just computed right here. Plug it in. So you crunch the math and you get A new equals 2.2 and 1 and 5, 1.4, 5, and 6, etc. Okay? All right? So basically, what have I done? I express inference and training in terms of matrices. I run a numerical example through the inference using the matrix notation, and then I did back propagation and updating the parameters using the matrix notation. In this class, I have not introduced a single concept which is new. Inference and training lecture explained what I just presented. All what we have done in this class, for one more time, we just represented the equation in the matrix notation, which abstracts the details and make it easier to understand what's going on in terms of math between the layers of the neural network. Okay, now let's generalize what we express, what we have discussed. Suppose you have a neural network, and in neural network you have many layers. deep neural network, sorry, and you have many layers. You have layer 0, layer 1, layer 2, layer 3, etc., etc., etc. Okay. Now, what we could do is that we can say, well, you know what? Let's just assume that we are looking at layer I, and I want to express the equations of that layer I. And if I am successful in expressing layer I, okay, let's say this is layer I, okay, and oops, sorry. If I'm successful in expressing layer I, then I can take these equations and use them for layer I minus one and use them for I plus one. So I want to derive or write down general equations for inference and training for any layer I. Okay. All right. So we're going to assume for layer I that the input, this is the layer, okay? The input is zi minus 1, right? All right. And of course, in case of input layer, right? Your z becomes x. Your zi minus 1 becomes x, which is the primary input for your neural network. The output of this layer is zi. So this is layer I. The input is zi minus 1, the output is zi. Of course, in the case of the last layer, this will be f, right? This will be the output of your neural network. So the special case for the input layer and the output layer, we have to be careful. For the input layer, zi minus 1 is the equals the x, okay, because they are the inputs to our neural network. And in case of zi, the output of the ith layer, if it is the last layer, then it will be f, which is the computed output of the neural network. Okay, and we assume that we have AI as for that layer. We have parameters, matrix I. I keep matrix I and bias B. Okay, this matrix I and vector bi. Okay, so all right, so this is the assumption here. All right, now. Okay, so applying conventional method, of course, it will be just a messy. I think you are sold by now. So let's talk about how we can express those forward and back propagation using these equations. Okay, so again, we said for layer I have my inputs here. Okay, um, for layer I, okay. My inputs here. Okay, so let's see if I get okay. So for this is my layer here. Okay, this is my layer I. Okay, so my inputs. These are the zi minus one, which are those ones. Okay, these are my inputs. My outputs is the zi, which is this one here. Those are my outputs. So basically, this is my layer right here. This is my layer. Okay. So again, we said for the input layer, for the zi minus one becomes our primary inputs, the x vector, and for the last layer, our zi becomes the output. This here is the activation function, ReLU, sigmoid, whatever you want. Okay. All right. Now, so the objective for layer I, we want to uh, compute these values, right? We want to compute these values, and the the output we can define this error for this function for this layer gi as the derivative of the activation function given this equation times delta L over Zi. Okay, where Zi, by the way, is coming from the previous layer. Okay, well, let's say, I'm sorry, let me, okay. delta L over delta Zi, it's coming from the layer which is the following layer. Okay. All right. Now, again, for the last layer, we know Gi equals Y minus F. Now we can compute delta L over delta Bi, and where this is the bias, as Gi, okay, which is what I derived here. Delta L over the AI, which is those are my parameters, as Gi times Zi minus 1 transpose. This is transpose. Okay, and then we can pass the error to the next layer. So now I computed, right, this delta L over delta bias and delta L over delta A, the parameters. Now I compute delta L over delta Z I minus 1. Okay, why? Because I want to pass it to the next layer. Okay, so what would that be? It is the parameter matrix A transpose times Gi, which is this one here. Now, once I compute it, I push it to the next layer. And this becomes now, I start to the next layer with this again, and I repeat with the same equations. Okay? So basically, this is a general formula to back propagate, okay, from layer to layer, knowing that this delta L over delta Zi has been computed earlier, okay, and I need to compute my delta L over delta B, B being the biases, and delta L over delta A being the parameters, and then pass the delta L over delta Zi minus 1 to the layer, which is layer that is before me in the neural network. Okay. So with that, the issue of doing and performing convolutional network becomes easy, because really in the convolutional network we have all these for the layers we have all these two-dimensional um, two-dimensional H and W for we call them feature, uh, these feature, extracted features, right? Features, extracted features, right? Extracted features from or a better name, feature map, okay, feature map, and those feature maps, they move from layer to layer. And as we move them down the pipeline, they have height and width. Well, this is good, two dimension, but then you get this third dimension. In fact, what we do as we move them down the neural network layers, we increase the depth, which is basically number of channels here. Okay, we increase those number of channels, and we reduce the height and the width of those feature maps, until at the end, what we get is just a width and a height of 1 by 1, and the depth, which is equal to the extracted features from the neural network and from the convolutional neural network. In other words, what we are saying here is that here we are looking at 3 dimensions. Okay, so definitely we need tensors. Definitely we need tensor notation, because we need to simplify the math of these things. Okay. Okay, so I hope what we have done, that we have not presented a new concept in terms of inference and training. All what we have done, we reformulated the equations in matrix notations, so that they are easier to follow in the inference and easier to follow in the back propagation step. And that is the end of my presentation. I hope you have enjoyed it and you learned something about expressing the equations in terms of matrices and tensors for neural networks. Thank you very much. And that's the end of my presentation.